Hello all. In today's lecture, we are going to see about DeMorgan's theorem. What is DeMorgan's theorem? Why we have to study this DeMorgan's theorem? And how is it related to us in our digital electronics? And how are we going to use it in our daily life? We are going to see each topic in detail in this lecture. But before we get into the topic, what is the first thing that is coming to your mind when you see the name DeMorgan's? Looks like we've heard this name so many times before and you're not getting it recalled now. Do you remember the term Venn diagram which you studied in your 9th and 10th class? There was a great mathematician named DeMorgan's who made you draw diagrams like this in your exams. For A intersection B. Similarly, he made you draw diagrams for A union B, A bar, etc., etc., etc. This is that same mathematician. When he was deriving all those equations, when he was deriving all those Boolean equations, he found out two theorems. And he felt like these two theorems can be used for digital electronics, mainly for simplifying our digital circuits. And that is how he gave two theorems to us for digital electronics. And those two theorems are named after him. And that's how the name DeMorgan's. Those two theorems are the one which we are going to study in this entire lecture. Theorem number 1 states the complement of your product is equal to the sum of the complements, and theorem number 2 states the complement of your sum is equal to the product of your complements. It might look a bit tricky, but don't worry, I'll explain you in detail so that you'll understand how it is getting framed, and we'll also prove to show you how this theorem works. Clear? And we'll also explain you with an example. Let's take theorem number 1. What does your theorem 1 states? The complement of your product term. What does it mean? Say if you have got two inputs like A and B, the product of both your inputs you have to take, and the complement of the product will give you the sum of the complement of each and every single term. In case if you have got, this is for two input, in case if you have got three inputs, say you have got three inputs A, B and C, what you will do? The product of all the input terms you have to take, and the complement of that product term is equal to the sum of the complement of each and every single term that is there in your input. Is that clear? We'll take for 4 input also. In case if there is 4 input, say we have got inputs like A, B, C and D. So the product of all the 4 inputs and the complement of it is equal to the sum of the complement. Sum of complement of each and every single term that is there in your input. This is theorem number 1. Clear? We are going to prove this also now. Understood the meaning of what they are explaining in your theorem? When they are asking you to explain theorem 1, how will you explain? The complement of your product of all the terms in your input is equal to the sum of the complement of each and every single term. Is that clear? What is theorem 1? Now, we'll try to explain this. Fine? Draw the truth table. How many inputs you have? You have got two inputs, A and B. Now, these two are my inputs. I have to prove my left hand side is equal to my right hand side. Right? Now, what is there in my left hand side? The product, complement of my product term. So take the product term first, A dot B, and then I'm going step by step. Clear? Now this is going to be my LHS. Fine? Similar way. What is there on my right hand side? It is A bar. I'm going to find A bar. I'm going to find B bar. And then I'm going to do a sum of the complement. Clear? A bar plus B bar. This is my right hand side. I have to check if my left hand side is equal to my right hand side. If my LHS, if it is equal to my RHS, then it means the theorem is working fine. Right? Fine. Let's do it. I have got two inputs. So how many combinations are possible for two inputs? 4 combinations. You very well know. 0, 0, 0, 1, 1, 0 and 1, 1. Right? This is my A and this is my B. What we have to find here? It is A dot B. What do you mean by A dot B? It is nothing but product term. A dot B meaning it is, we have to do a multiplication. Right? Now do the multiplication. I have A here, I have B here. Do a product of these two. 0 into 0 is what? 0. 0 into 1 is what? Anything multiplied by 0 is going to be, this is something like 0 into 1. Anything multiplied by 0 is again 0. So anything multiplied by 0 is again 0. Here again 1 into 0. 1 dot 0. This is nothing but 1 into 0. Again anything multiplied by 0 is again, it is 0. So again for this term again it will be 0. 1 into 1. 1 into 1 is 1. Clear? Now I found A dot B here. What is my next step? It is A dot B the whole bar. What do you mean by bar? Bar meaning whatever value you have to take a complement of it. If it is 0, it becomes 1. If it is 1, it becomes 0. Right? See, if A is equal to 0, what is A bar? A bar will be 1. Clear? In case, if B is equal to 1, what is my B bar? B bar will become 0. Whatever value you have, if you take a complement, that value will get toggled. If it is 0, it will change to 1. If it is 1, it will change to 0. Clear? Now, we have A dot B here. Here, we have to find A dot B the whole bar. Fine? So, for A dot B, if it is 0 here, A dot B the whole bar will become 1. If it is 0, it will become 1 since we are taking a complement. Is that clear? Here again, here we have got a 0 here. If we are taking a complement of it, it becomes 1. Here again, it is 0, so it will become 1. Here we have got 1. The complement of 1 is 0. Is that clear? Now, this is my LHS. That is my left hand side. Fine. Now, let's do for the right hand side. A bar. This is my A. I have to find A bar. In the same way, in case of A is 0, what is my A bar? A bar is 1. The complement of whatever value is there in A, that will become your A bar. Clear? Here, if it is 0, for A bar, it will become 1. Clear? Here again, A is 0, so A bar, it will become 1. Clear? Now, here, A is 1, so A bar will become 0. Here, A is 1, A bar will become 0. Understood? In a similar way, do for B bar again. We have got B input here, we have to find B bar here. B, it is 0, so B bar will become 1. Very good. Here, if it is 1, what is your B bar? It will become 0. The complement of it. Is that clear? Here, B is 0. So, B bar will become 1. Here, B is 1. So, your B bar will become 0. Clear? Now, we have found A bar. We have found B bar. What is the last step? It is A bar plus B bar. This is normal addition. Fine. We have got A bar input here, B bar input here. We have to sum up these two for finding A bar plus B bar. Do the sum. 1 plus 1 is 1. Clear? 1 plus 0 is 1. 1 plus 0, it is again 1. Fine. Again, 0 plus 1 is, that is again 1. 0 plus 0 is 0. I found my RHS. Now, check whether my LHS is equal to my RHS. Here, for the first case, here again it is 1, here again it is 1. Condition satisfied. Here again, both are 1. Here again, both are 1. Here again, both are 0. Meaning, the values in my LHS is same as the values in my RHS. Hence, the theorem is proved. Is it clear? We have proved our first theorem. Understood? After finding the truth table, what is the next step? We have to design it also. Do the designing part. We have got the Boolean expression here. So, based on that, we can design it. Now, what is my LHS? It is A dot B the whole bar. A dot B. For A dot B, what does it mean by A dot B? It means it is a product term. So, for product term, which gate you will be using? You will be using an AND gate. Right? In case, if there is a complement, then what gate you will be using? It is NAND gate. Right? Now, design it. How many inputs we have got? We have got 2 inputs. What are the inputs? It is A and B. Clear? A and B. What have I done here? It is a product term. So, for product term, which gate I will be using? I will be using AND gate. So, I am taking an AND gate. And I have got a complement also. So, for a complement, how do you mention? You will be mentioning it with a bubble. Clear? So, what is the output of it? Here, this is nothing but A dot B the whole bar. Understood? This is my LHS. Left hand side. Fine. Now, this is equal to, what is there on your right hand side? It is A bar plus B bar. So, for A bar, A is here. For A bar, I am going to take it to a NOT gate. Clear? So output of this will be A bar. Similar way for B again. This is my B input. I'm going to take it to a NOT gate. So the output of NOT gate will be B bar. Clear? Now A bar plus B bar. For doing a sum, which gate you will be using? For A plus B, which gate you will be using? You will be using an OR gate. Right? So the output of these two terms, you have to take it to an OR gate. Clear? So this is A bar. One input is A bar, the other input is B bar. Since it is an OR gate, I'll be doing a sum. Understood? Clear? This diagram can also be drawn as this is again same as this term. On the inputs, I've got a bubble. It means on the input, I have negated my input. Clear? I have complemented my input before feeding it to my OR gate. Clear? So what do you understand from here? Theorem 1 states my NAND gate is equal to my OR gate with negated input. Negated input meaning complemented input. Is that clear? Understood? Now, coming to the interesting part. You might be thinking like, why am I studying all this? Where am I going to use it in my real life experience? In fact, even without your knowledge, you're actually making use of this DeMorgan's theorem in our daily life. One of the best real life example is data privacy and security. Say for example, you have got all the confidential data inside a system and you have kept that system inside a room. This room doesn't have access to everybody. Only selected members have got access inside the room. Fine. Those people who are unauthorized people, if they are trying to enter inside the room, then an alert message goes to the owner. Clear? And even after getting in, if he has not got the authentication, that is, if he doesn't have the username or the password, still if they are trying to open, then again an alert message goes to the owner. Clear? Now, rather than doing a complete check twice, like first time doing a complete check whether the person is authorized or not, again doing the same set of check to see whether he has got the authentication or not, instead of that, on using DeMorgan's law, it will combine both the process so that your decision making gets smoother and faster. Let's see how it is working. Now, let's assume A as authorization. Fine. And B as authentication. And I want this as my output. Let this be the alert message that is going to the owner. This is my LHS. Either I can take LHS or I can take RHS. Both are one and the same. So any one data you can take it for checking. Fine. Now consider the person who is trying to enter in, he doesn't have authorization and he doesn't have authentication also. Still, if he is trying to get in, then an alert message goes to the user. Understood? If it is 1, it means an alert message has been sent to the user. Fine? If the data is 0, it means he doesn't have that access. First one, A refers to authorization. So A, it is 0. It means he doesn't have authorization, and B corresponds to authentication. Here B is again 0, which means he doesn't have username and password also. But still, he is trying to get the access inside the room to access the machine. If that is the case, an alert message, it will go to the owner. Fine? Now, again, the person doesn't have authorization. That is, he cannot enter the room even though he has got the username and password. If he is not able to enter inside the room itself, if he is not been authorized to get inside the room itself, again an alert message goes to the user. Say for example, that person was there in the team and for some reason he is being chucked out of team. Fine, though he has a username and password for that particular system, his access has been revoked, and still if he is trying to get in, then automatically a message goes to the owner. Clear? Now, your third condition. The person has got authorization. That is, he is able to get inside the room. Fine? But he doesn't have authentication. He doesn't have the login and the password. Say for example, the system which has got the confidential matters can be accessed only by the family members. Though an employee, meaning selected employees, are given access to enter inside the room, but they don't have access to open the system. Clear? That is this case. The employee has got access inside the room, That is, he has been authorized to enter inside the room, but he doesn't have access to open the owner's laptop. But still, if he is trying to open, again an alert message goes to the owner. Is it clear? Now, the final case. The person, he has got authorization, that is, he can enter inside the room, plus he has got access to open the system also. Fine. If he has got both the access, then no messages will be sent to the owner because he is a trustworthy source. Clear? Now, rather than doing a two separate checking for taking a decision of whether to send the message to the owner or not, DeMorgan's law has combined. This is one real life example that we are practically using it in our daily life. I hope you might have understood how this DeMorgan's law is working in our real life. Now we'll go to Theorem 2. What does Theorem 2 states? Theorem 2 is what? The complement of your sum term is equal to the product of the complement of every single input term. That is, A plus B, the whole bar is equal to A bar dot B bar. Same like how you defined your theorem 1, we have to define theorem 2 as well. Depending on how many input variables you have. In case, if you have two input variable, as in this case, then you have to sum up both the input variables and then you have to take a complement. Clear? This is equal to the product of the complement of every single term, every single input variable. Say if you have got three variables in an input like A, B and C, then sum of all the three variables and its complement. The complement of the sum of all the three input variables is equal to the product of the complement of every single input variable. Clear? In case if we have four variable, come on, tell me for four variable how it will be. The complement of the sum of all the four input variables is equal to the product of the complement of every single input variable. Is it clear? What is theorem number 2? Now, let's try to prove this using truth table. How many variables are there? Two variables. So, I am taking both the variables A, B. Now, what is my LHS? It is A plus B. I am taking it step by step and A plus B the whole bar. This is my LHS. Right? Now, I have to find my RHS also. On my RHS, what all variables I have? It is A bar, B bar, and then the product of A bar dot B bar. Is it clear? Now, this is my RHS. And these two are my input. A and B is my input. Since I have got two inputs, how many combinations are possible? Four combinations. Give all the combinations 0, 0, 0, 1, 1, 0, 1, 1. Is it clear? Now, here it is A plus B. So, take both the variables and do a summation. That is A plus B. A is 0, B is 0. So, 0 plus 0 is 0. Here, 0 plus 1 is 0 plus 1 is 1. Right? So, 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is again 1. Is it clear? Now, what is the next column? It is A plus B the whole bar. So, what is the meaning of it? Whatever values I have for A plus B, I have to take a complement of it to get my A plus B the whole bar. Complement in the sense, if A is equal to 0, my A bar will become 1. Clear? Now, this is A plus B. So, whatever values I have here, the complement of it will come in A plus B the whole bar. Right? If it is 0, my output here will be 1. If it is 1, my complement of 1 will be 0. Again, if it is 1, the complement of it is 0. If it is 1, the complement of it is 0. Clear? Now I have got all my values for my LHS. Fine. Now start filling the next column. It is A bar. A bar in the sense whatever values I have for A, the complement of it will come in A bar. Check for A, it is 0 here. So the complement of it is 1. Here again, it is 0. So the complement of it is 1. Here, it is 1. So the complement of it is 0. Here again, it is 1. So the complement of it is 0. Clear? We have done for A bar now. Similarly, do it for B bar. B, we have it here. Take the complement of B so that we get B bar here. Fine. Here it is 0. So the complement of 0 it is 1. Here it is 1. So the complement of 1 is 0. Here it is 0. The complement of 0 is 1. Here it is 1. The complement of 1 is 0. Is that clear? Now, what is the final column? It is A bar dot B bar. A bar I have it here. B bar I have it here. I have to do a product of these two terms to find this last column. Right? Now do a multiplication. Dot meaning it is multiplication. Fine. 1 into 1. 1 into 1. 1 into 1 is what? It is 1. So 1 into 1 is 1. 1 into 0. 1 into 0. Anything multiplied by 0 it is 0. So this will become 0. Here again 0 into 1. 0 into 1 is what? Anything multiplied by 0 it is 0. So again it is 0. Clear? Now 0 into 0. 0 into 0 is again 0. Clear? Now check whether your LHS is equal to or RHS. If both are same, then your theorem is verified. Fine. Now check both the terms. LHS and RHS, the first term is 1 and 1. Both are same. Here it is 0 and 0. Same. 0 and 0 same. 0 and 0 same. It means we have proved our theorem 2. Now, after proving your theorem using truth table, what is the next step? We have to do the design procedure. How do you design? We design it using logic gates, right? Based on the Boolean expression that we have it here, based on that we are going to design. Clear? How many inputs you have? You have got 2 inputs. What are the inputs? It is A and B. What is the term that you have used here? Plus. So for plus, which gate you will be using? You will be using an OR gate. Clear? Now, A plus B. A plus B, so I have used an OR gate. But I also have a complement on top. So for a complement, you will be representing that with a bubble. Clear? So what is the output of it? It is A plus B the whole bar. Understood? So this is my LHS. Now, give the RHS. RHS is what? A bar dot B bar. Dot product, how do you represent? You represent the dot product with AND gate. Clear? Do your RHS. It is A is here, but I'll be feeding it inside a NOR gate to get my output as A bar. So I've got A bar here. In a similar way, for B, input, I'm going to feed inside a NOR gate so that my output is B bar. Now A bar I've got, B bar I've got, A bar dot B bar. For dot product, which gate you will be using? AND gate. So the output of these two, I'll be feeding it inside a AND gate. Clear? So the output of this is A bar dot B bar. One input is A bar, the other input is B bar. So the product of these two will give my output. Clear? This is my RHS. This can be represented as, what do you understand from here? NOR gate is equal to AND gate with negated input. Is that clear? Same as your theorem 1. In theorem 1, how did we prove? NAND gate is equal to OR gate with negated input. Right? Similar way for theorem 2. It is NOR gate is equal to AND gate with negated input. Is it clear? Negated meaning it is inverted input. That is, you have a bubble on both your inputs. Understood? Is it clear? This is all about theorem 2. This is one of the important topic. In fact, frequently in almost all the semester exams, this is one question which has commonly been repeated. I hope you are clear with DeMorgan's theorem. Let's sum it up. In today's lecture, we saw what a DeMorgan's theorem is and little bit history about how De Morgan gave these two theorems to digital electronics for simplifying our digital circuits. And we explained about Theorem 1 and Theorem 2, and we tried to give the definition of both the theorems based on the equation. And we also tried to prove both these two theorems using truth table, and we also try to design them using logic gates. And finally, you have to conclude, like, from the design, what are you inferring? Fine. And we also try to relate this De Morgan's theorem with our real life examples. I hope you're clear with this topic. If you find my lectures useful and informative, please do like, share and subscribe. And don't forget to click the bell icon for getting the notifications on my upcoming videos. Thank you.